So, greetings of the day to all of you. So I welcome you all to another lecture or doubt clearing session on of the course Fundamentals of Electrical Engineering, being taken by Professor Debapriya Das, and I'm Swastik Sharma, a TA for that course. So let's start.
Recording in progress.
Okay, so I don't think that's going to be an issue now. Okay. So last week we were discussing three-phase circuits. So we'll continue from that. So today we'll discuss three-phase circuits, how to calculate power in a three-phase circuit. Then we'll move on to a more to the next topic in hand, which is magnetic circuits, right? So let's start with three-phase circuits first. So we know so we first want to know how power is how power is calculated for a three-phase circuit. So it's fairly simpler concept. Like for example, the instructor has shared notes on it and how the power is calculated. I'll just quickly tell some interesting facts about it, because if I solve everything, it'll take time, right? So so power in terms of phase for a three-phase circuit is given by Vp Ip cos theta, where of course the P subscript denotes that these are phase quantities, right? And cos theta is our power factor. So this is how this is active power. I should actively mention this too. So this is active power given in watts, right? And in terms of line voltages or line currents, we know that for star, the line currents and phase currents are same, while for delta, the phase voltages and phase line voltages are same, right? So if we use that, we'll come across this formula, right? We'll cos theta. So so this is how it's written in terms of line voltage, line parameters, line voltages and currents, right? Now, this is active power. What is Q? Q is nothing but it's simple, right? It's Q. It's in 3 Vp Ip sine theta, or under root of 3 times VL IL sine theta, right? So the that's how we denote the power, and this is reactive power. It's given in VARs, right? Oh, sorry, it should be right. So there's one more quantity called apparent power. It is nothing but E plus JQ. So I've already told you how the power triangle look, and where all of these individual quantities stand. So that's how they're written, and it could be written as 3 Vp Ip theta, right? It's a phasor quantity, and it's given in terms of volt amperes. Okay, so that's how usually you write uh, that's how usually power is measured for a three-phase circuit. Let's move on to measurements, right? So, so there are so two properties mostly. So first of all, for a balanced um, system, there's a concept of one wattmeter method. And for unbalanced, there is two or three wattmeters method. So as you can, as you can notice that for a balanced system, if we use only one wattmeter between the phases, we can calculate the power for the whole circuit. But for an unbalanced system where the voltages and currents are not in phase, so are not 120-degree apart. So for that, two or three wattmeters are at least needed, right? So let's see how. So if I show the working of one, you may calculate for it yourself. You'll notice that the concepts are fairly same, and that's how you can calculate for the individual components. So for a 2 wattmeter method, so first of all, before going into the um, into the method itself, you should know that since the instructor has taught 2 wattmeter method, you should focus on the concepts being derived from it, and you can use the similar concepts for and apply it to 3 wattmeter or 1 wattmeter method too. And you'll notice and you'll appreciate why I've written that 1 wattmeter method can only be applied to a balanced system. So let's say we have a three-phase, three-wire power supply. And so this is A, B, and C, right? And we have a star connected load. I should have drawn it simply. Let's try it like this. Right. So this is a star connected load, right? So this is the neutral. It's a balanced load, Z by Z by, right? So what we are so what usually a wattmeter has? A wattmeter has a current coil which is placed in series in a phase, and a pressure coil which is placed between two phases. Yes. So let's so this is a current coil, and that's how our pressure coil will look like. So this is wattmeter 1, and this is wattmeter 2. Right. And we've assumed that the loads are balanced. So let's say that ZY is nothing but Z at an angle of theta. So now what we want is to calculate power, we need current that is flowing from that phase, and we need and the voltages, right? We can assume that it's a three-phase, three-wire system, VAB and VBC, right? So this is positive, negative, and negative, right? So that's how the circuit looks like. Now, now to calculate it, we know we can easily calculate IA, right? I is what? For a phase value of that voltage or a phase voltage, which is an VN, we'll consider this as reference. Let's start, right? Now we know line voltage leads phase voltage by 30 degrees, right? So we know this would become, oh, sorry, minus 30 degrees, right? And we know since it's going to lead it by 30 degrees, the value is VAB. VAB is nothing but root 3 times VN, right? So we can write it like this. So we know that it's given at an angle of Z angle theta. So IA could be written as VAB upon Z angle of minus theta plus 30 degrees. So that's how our IA would look like. Now, if we try and denote this all in a phasor diagram, how would it look like? Like, let's see. So we had VN as a reference, right? Which was at an angle 0. And we told that VAB leads that by 30 degrees. Also, we know since IA is nothing but VAN upon the impedance Z, so it would lag the voltage, phase voltage by theta. So to calculate power, we know that the VAB is leading the voltage the current by theta plus 30 degrees, right? So power 1 or the voltmeter 1 reading can be written as what? It can be simply VAB times IA cos of theta plus 30 degrees, right? Now let's see for this wattmeter second. Let's continue over here only. Let's draw this in the same phasor diagram. We won't calculate anything. We'll just use this phasor diagram to come up with what would happen with that uh, wattmeter, right? So we know VCN will lead VN by 120 degree and VBN will lag VN by 120 degree. So that's there. So also we know that IC will lag. So what are the quantities we are interested in? We are interested in VBC and IC, right? Because that's what the wattmeter is measuring and trying to come up with the reading for that wattmeter. So IC is lagging VCN by theta. Similarly, VBC. So this is 120 degrees, right? If I move 30 degrees ahead, it would be 90 degrees. So that means VBC is perpendicular to VN. And that's what usually happens too. So, what we really are interested in is the difference between the phasor difference between phasor angle difference between IC and VBC, right? So let's superimpose over here. This would be VCB, right? Minus of VBC. And what would this phase angle be? Can anyone tell me? So how can we get what this phase angle difference between IC and VCB is going to look like? No? Okay. No one's going to say? Okay. So there's only one person. So uh if we calculate VCA, how would it look like? It would lead VCN by 30 degrees. Am I right? So if this whole quantity is 30 degrees, that means if I take this, for example, um, this is VCA, right? So this is leading it by 30 degrees. So that means this whole angle has to be 30 degrees, right? Am I right? You can ask doubts if you don't understand. So if VC and I superimpose over here, this is what? 30 degrees. So this angle has to be 30 degrees as well, right? Because in between those two quantities, what would be the difference? 30 degrees. So if this is 30 degrees, that means the difference between VCB, the phase angle difference between VCB and IC is 30 minus theta, right? So that means P2 or wattmeter 2 reading would look like VCB times IC cos, sorry, cos of 30 degrees minus theta, or we can write it as VCB IC cos of theta minus 30 degrees, right? So now this would, here I wrote it like this. So VAB and IA are both line currents and line voltages, right? So we can write VL, IL since it's a balanced system. These quantities can be written like this, right? And similarly, this will also be line current and line voltage. This comes out to be like this. So now I'm saying that PT, which is equals to under root 3 VLIL cos theta, is equals to P1 plus P2. This can be proved, right? So let's take right hand side first. So P1 plus P2 is what? VLIL cos theta plus 30 degrees plus theta minus 30 degrees. So if you add these two terms, what will you get? You'll get cos of theta cos of 30, which is under root 3 times VLIL cos theta. So, sorry, this would be 2, right? Yeah. So this would be cos theta. So that means that to calculate total power for a balanced system, we can use a 2 watt meter method and we'll get the solution, right? And the individual wattmeter readings are what? VL will calculate this theta plus 30 degrees, while the wattmeter 2 will calculate cos of theta minus 30 degrees. Just remember these three quantities because to solve questions, this is what you are going to use. So this is about 2 wattmeter method. So any questions up until now, or should I move ahead? Okay. So this is for active power. So with 2 wattmeters, we calculated active power, right? We calculated the meter readings and added them. What about reactive power? So let's do one thing. Let's subtract the 2 wattmeter reading, right? So what is it? P1 minus P2. It comes out to be VLIL cos of theta plus 30 degrees minus cos of theta minus 30 degrees. Sorry, it should be P2 minus P1. Otherwise, the term will be negative. So that means it is VLIL cos of theta minus 30 degrees minus cos of. So if you calculate it, it will come out to be sine theta. So that means QT is what? Root 3 T times VLIL sine theta, right? which can be written as root 3 times P2 minus P1. So with the same watt meters, if you subtract those two readings and multiply it by root 3, you can calibrate that instrument to calculate the reactive power as well for the circuit. So this is an interesting uh, conclusion. And what else? Okay, so that was this QT. So any other thing that we got? So 2 watt meter method. So let's solve some questions so that you are able to solve it for your assignment too. So let me know in between by muting yourself, unmuting yourself if you have doubts. So there were some questions from previous assignment that I wanted to discuss. We'll do it at the end because this is not relevant. So the question is saying that 2 watt meters which are connected to measure the total power of a three-phase system, which is supplying a balanced load, read minus 21 kilowatt. That means P1 is what? Minus 21 kilowatt, and P2 is 81 kilowatt. And the total apparent power taken by the load is S kilowatt ampere, and the power factor is PF. Find the values of S and P. Okay, so as I told, P1 plus P2 is root 3 times VL cos theta, and P2 minus P1 is VL sin theta. So if you divide both, what will you get? You get P1 P2 on P2 minus P1 root 3 times cot theta, right? So that means theta is nothing but cot inverse 1 upon root 3 P1 plus P2 upon P2 minus P1. So we are required to find cos theta first. So let's do cos theta, which is cos of cot inverse 1 upon root 3 P1 plus P2 upon P2 minus P1. So if you plug in these values, you'll get, let's do it. You can also do it on your calculators. P2 was 81. So cos theta came out to be 0.3216. So we got the power factor, which was, and there's only one part, B. So B is the correct answer. For S, what you have to do is, you know the total power, right? So ST is nothing but PT cos theta plus J time QT sin theta. And you can calculate this and write in terms of polar form. Whatever is the magnitude of these, it will be equal to this answer, right? Because there's no other answer. So you can use this to calculate the answer for this. So the answer is B. Let's move on to next question. So it's saying that there is a three-phase balance load which has a power factor of 0.8. Okay, that means cos theta is 0.8. It is connected to a balanced supply. The total power consumed by the load is, so PT is also given, which is 20 kilowatt. Sorry, this shouldn't be like this. This would be simply PT. JKT. Yeah. So PT is given as 20 kilowatt, right? The power is measured by 2 watt meter method. The readings of 2 watt meters are. Okay, so we can use these two equations to calculate the cos theta one equation and PT equation to calculate this whole thing. Let's do it. So we know PT is what? Yeah. So PT is P1 plus P2, which is nothing but root 3 times VL IL cos theta, right? So we know this thing which is 20 kilowatt, and we also know that cos theta is 0.8. So we can make use of that equation. So theta can be written as what? Cot inverse 1 upon root 3 P1 plus P2 upon P2 minus P1, which is equals to cos inverse of 0.8. Cos inverse of 0.8 is what? 36.87 degrees. So that means if I do, so 1.333, right, is 1 by root 3. P1 plus P2 we know is 20, P2 minus P1. So we get two equations, right? So P2 minus P1 is what? 20 upon 3. So it comes out to be 8.66 kilowatt. So P1 and P2 are, so two equations, two variables, right? P1 plus P2 is what? 20 kilowatt. So if you solve this, you'll get P2 as 14.33 and P1 is 5.67, right? So the answer is C. So the questions, if you can see, are fairly very simple. You just need to know how the two readings can be used to calculate what's required for our questions, right? Let's move on to the next question. This is a good question. This is based on 1 wattmeter connection. So um, let's first look at how 1 wattmeter connection is supposed to be, right? Let's take the same. So any questions up until now? You can please feel free to unmute yourself and let me know. So instead of this, what they're doing is they don't have a second wattmeter, right? This is so what they have. What they are doing is they are just simply connecting the current coil in series with the phase A, and the pressure coil is being connected. Just a second. Yeah, and the pressure coil is being connected across across two phases, that is B and C or A and B, right? So let's see how the circuit would look like for that. So this is 1 wattmeter pressure coil, right? So so what you require is you require VBC, right? And you require I. What is the phase angle difference between the two quantities, VBC and IA, right? Because the pressure coil is measuring VBC and the current coil is measuring the current IA. So let's see. We know, let's take phase voltage across A as a reference. We know the current IA will lag this by some theta, which is dictated by the this load, right? So, and we also know that line quantities lead phase quantities by 30 degrees. So this is now the question is, since So yeah. So this is how these two quantities will look like. Now, but now what we are required to find is the phasor angle difference between IA and VBA. Sorry, VBC. So if VAB is like this, so the VCA leads it by 120 degree and VBC lags it by 120 degrees. That means it lags the phase voltage VAN by 120 degrees. So that means the phase angle difference is nothing but 90 degrees minus theta, right? So if we write the wattmeter reading is nothing but VBC times IA cos of 90 degrees minus theta, which can be written as this. These are all magnitude, right? Remember, which can be written as sine theta, right? So that means the wattmeter is doing nothing but calculating, kind of trying to calculate. It can be calibrated to calculate our reactive power, which is given by √3 times its reading, right? So for a 1 wattmeter method where we connect it between two different phases, like current coil is in phase is in series with the A phase, while the pressure coil is between two phases B and C. It would measure the it could be calibrated to measure the reactive power, right? So the question is trying to ask us the similar question, but with a twist. Here it's saying that the phase sequence is, yeah, the phase sequence is, just a second, it's not visible, right? It's saying the phase sequence is ACB. That means instead of B lagging phase volt, if instead of B phase voltage lagging A phase voltage, it now leads, right? So that means this sequence would look something like this: VAN, VN. Always remember to know how these phase sequences are written. Just move anti-clockwise, right? If it's written ACB, so in anti-clockwise it will be ACB only, right? That's how you just make this diagram. Okay, so yeah. So now what we are required to find is we are required to find, so the wattmeter one reading will be between VBC and IA, right? So that's what we are required to do. Now we know VAB is what it leads. Sorry, just IA will be at an angle theta, right? This we all know. And since VA, so the phase sequences are changed, right? So that means line voltage VAC or VCA will lead, we should write VAC. VAC will lead it by 30 degrees. So that means what would be these individual quantities? These would be right. So that's how these individual quantities would be. Sorry, this would be VBC. This is VAC, then VCP, and then VPA. So that's how these individual quantities would look like. So that means VBC is what? We can extend this. This is VBC, and we are required to know what um, this voltage phase angle difference is. So let's think. This is leading it by 30 degrees, so that means this is 90. 30 degrees, right? This would be also be 30 degrees. So, just a second. Is 120 degrees and 30 degrees. This will be 30 degrees, right? Hmm. Yeah, this whole angle is 30 degrees. So this would be 30 minus theta. So I think this is 30, right? So this would be 30 minus theta. Hmm. So if you see, right? So this whole angle is 90 degrees. Just give me one. Small as one. Yeah. So this would be 30. The difference between these two would be 30 degrees, 30 minus theta degrees. So so that means the wattmeter one reading is nothing but VBC magnitude times IA magnitude cos of 30 degrees minus theta. So if someone can quickly calculate and let me know what is it. 440. Oh, we haven't calculated IA. So let's first calculate what IA is going to be. Now we know VAB is what? If we do VAB is IA times Z minus IB times Z, right? So this is IA minus IB times Z, which is nothing but IA. Since it's ACB sequence, now IB will lead it by 120 degree. So will lead it by 120 degree, and Z is given by 4 plus J 15. So VAB is 440 at an angle 0. Right. So this would be what? Under root 3 times IA. So 4 plus J 15 can be written as 15.52 at an angle 75.1. This is minus 30. So this would be root 3 times 26.88 at an angle of minus 30 plus 75 is 45.19. So now IA can be calculated easily. So what is IA? 440 angle minus 45.1 divided by 26.88. So IA is nothing but 16.37 angle minus 45.1. So let's plug it in W1. So W1 is what? VBC, which is 440 into 16.37 cos of 30 degrees minus of 45.71. Right? So if you calculate it, it's going to be just something wrong. Also, oh, sorry. Hmm, hmm, hmm. So this is 30 degrees leading DC. This will be degrees. It's something wrong somewhere. Hmm. Swing is 90 degrees. This is correct. This is 30 minus theta. Oh yeah, sorry. Since I've already taken direction, why should I write minus over here? Sorry, excuse me for this mistake. So yeah, so what was coming out to be wrong is I've already assumed direction here, right? So theta is already negative. So I don't have to use this negative sign and negate it over here. That's what was causing it. Yeah. So that means the answer would be 6954.1 watts. Right. So watt meter one reading is this. Now we know mm, for the full, so the total reactive power QT is what? Under root 3 times W1, right? So if we do it, we get 12044.8654 watts. So now the question says W1 measures the per phase active power. So this is wrong. It doesn't measure per phase active power. The total active power consumed by the three-phase load is approximately equal to 12049 units, and the reading is approximately 6957, and the total reactive power is this. Now, since the total reactive power we calculated is 12044, this is also wrong. C says the per phase reactive power consumed by the load is approximately equal to 12049, and the reading of W1 is approximately equal to 6957. Okay. The total active power consumed by the three-phase load is approximately equal to 3213. The total reactive power consumed by three-phase load is equal to under root 3 W1, and the reading of W1 is approximately equal to 6957. Okay. So yeah, now we need to calculate the total active power to distinguish between these C and D options. A and B are wrong. So let's see. How can we calculate the active power? So I got a bit confused during the lecture. So what they're asking is the active power consumed by the three-phase load, right? So what I was trying to calculate was, yeah. So let's do it. So what they've given is, yeah. So there's this only the 4 ohm resistor will dissipate active power, right? We know that only the resistor dissipates the active power. So what is it going to be? It's for the total reactive power, right? I should write total active power. Sorry, total active power. It's nothing but since it's balanced, so I'll just calculate along the A phase into 4, right? 3I square R. So what is it? So it's 3 into 16.37 squared multiplied by 4, which is nothing but 3215.7228 watts. So this is what it comes out to be. So it's approximately equal to 3213, right? So, but I still have one doubt about this question, that they said that it's the per phase reactive power consumed by the load is approximately equal to 12049 units. But it's not the per phase; it's the total active reactive power consumed by the load, right? It's under root 3 times W1. So I don't know. I'm still a bit concerned with these wordings, but yeah, the closest the answer is C. D is wrong. Okay, let's do magnetic. So let's start with magnetic circuits. It's already time. Hmm. So right till now we were discussing how electrical properties of a circuit are change how we or deliver how we so it's how electrical quantities we were talking about. Now we'll shift our focus to magnetic quantities. So we know when a current carrying conductor is placed on somewhere, it produces a magnetic field around it. This is true for any current carrying conductor. So let's say that we have let's say that there is this page, right? Let's assume there is this page. This cross means that into the page, and a dot means out of the page. So if we have some current carrying conductor, and the current is coming and current is something like it's going into this page, it produces what's called magnetic field around it. So I'm not drawing to scale, it would be uniform. So this is how the magnetic field looks like, which surrounds this current carrying conductor. Now, what usually happens is whenever some other conductor is placed inside this magnetic field, it experiences a force, right? So that's how that's the whole working of electromagnetic systems such as generators or motors. So when they are kept in a current carrying when they are kept in a magnetic field, they experience some force on it. So now this magnetic field helps in coupling two or more systems together. Hmm. So they help in coupling the system together. So that's how that's where this property is exploited. Now so now let's talk about magnetic force, because this magnetic force is nothing but it moves to the tangent of this radius of this magnetic field. Like for example, for this is how the magnetic force will look like. The magnetic force is given by H, which generally means magnetic field intensity, and it decreases as we move outside the circle, outside this magnetic field lines, right? So it's given by nothing but I upon 2 pi r. So this is magnetic field intensity. As R increases, this magnetic field intensity will decrease. Right. Now, there is one more thing. There's this concept of flux density. Flux density is the property of medium, right? So it's a property of medium in which this flux intensity is established, right? So it's nothing but B times mu naught H, right? So that's how this whole flux density is denoted. It's denoted by Weber per meter squares or Tesla. Now, so I am just going through what are the various quantities. I expect you to go through the lecture material provided by sir, because the classes lesson I have to cover the sample problems for this too. So now, this is flux density. Also, for a media, so this is mu naught is generally for um, uh, it's uh, it's um, it's generally for free space, right? And the quantity is given by 4 pi into 10 raised to power minus 7. It would be Tesla Weber per meter square on ampere meter, right? So this would be Weber per meter upon ampere. So that's how this mu naught is written. Then this mu naught is called permeability constant. So for a free space, it's given by this quantity. For, let's say, for any other space, we define a relative permeability. This is called relative permeability, which can be written as this. So for any other media or medium, this is how we denote this the permeability constant, which can be written as this only, right? There's also flux. So we'll move on to how the parallels are drawn between electrical circuits and magnetic circuits, but just be patient and listen what exactly these quantities are. Phi is nothing but the flux density multiplied by the area of the medium, right? This is given in Webers. And let's drop comparison of magnetic circuits So let's say that we have this toroid core in on which a coil is wounded with n turns, and in this coil a current is flowing, which is given by I terms, and there is from the mean flux path a flux flows inside the core and connects the parts of the core, right? So how exactly are um, so how exactly do these how exactly parallels are drawn between electrical circuits is what I'm going to explain, right? So let's say that since there is a flow of current, so there is an establishment. So for each conductor, we can see that there will be an intensity, right? Magnetic field intensity for each conductor, because there are n turns, n times wound. This magnetic field intensity would be n times, right? So this is generally given by H is given by n times I divided by the mean flux path, which is 2 pi r, right? And this Ni is nothing but our magnetomotive force, which is called as MMF. And this magnetic field intensity can also be written as Fm upon L, where L is the mean flux path, which is given by 2 pi r, where r is the radius, right? Now the flux density of the core is nothing but B, which is mu times H, which can be written as mu times Fm upon L, right? Again, the quantity is Weber per meter square, and the flux is P times A, which can be written as mu naught Fm upon. So this can also be written as Fm upon L upon A mu. Right, I just removed those two terms A and mu from the numerator and divided them from the denominator, right? So this term is called as reluctance, which is denoted by R, right? And hence phi can be written as Fm upon reluctance or permeance Fm. This is called permeance. So if we draw parallels, so how would the circuit look like? For electric circuit and magnetic circuit, we knew the EMF is the driving force in that circuit, right? In electric circuits that are usually given in terms of E volts, and in magnetic circuits, the MMF is the driving force, which is given by Fm. Now, there is a concept of resistance which obstructs the path of flow of current, right? This is denoted as rho L upon A. But for our circuit, reluctance is what obstructs the flow of flux. So this is given by L upon mu times A, right? So here current flows, which is given by nothing but E by R. Here flux flows, which is given by Fm upon R, right? So that means if we write it in terms of equivalent DC circuit can be represented, which is nothing but so that's how we draw parallels between between magnetic circuits and electric circuits, and this is usually this thing helps in usually solving questions fairly quickly. You can just calculate reluctance and then magnetic motive forces, and then flux is nothing but Fm upon R. So you know how to that's why you know how to solve these questions. Now, so there's a concept of fringing effect. So when we have a core and it's displaced, like for example, an air gap is introduced in it, we assume that the flux which flows like this will continue flowing like this, right? But that's not the case. The flux flows like this. That is, as it gets an air gap, it experiences a non-uniform magnetic field, and that's how the intensity decreases as we go away from that center point, right? So this usually is called fringing effect, and the this creates a non-uniform air gap flux density, and hmm, let's move on to another property, hysteresis. So hysteresis is generally the BH curve. Hysteresis is usually drawn to know what's the effect of BNH on each other, that is magnetic field intensity and magnetic flux density on each other. So if we draw for a ferromagnetic core, smaller. So I've not drawn it to scale, but that's how usually a BH curve looks like. This shows that even if we continue to increase the current through a conductor, the magnetic flux density or the flux will saturate. It will come to a point where it won't increase. Like for example, if we move here, what's happening? H is nothing but I upon 2 pi r, right? If you're increasing the magnetic field intensity, the B flux density starts increasing, but there comes a point where usually it becomes saturated. So that's how we usually. So the greater the area, the easier or the faster the the magnetic flux density will saturate. Now, at points where each of these quantities are zero, have a very interesting meaning. Like for example, at h equals to zero, there is this Br. This is nothing but a remnant flux density, or this is the flux density which remains when we have de-energized our conductor. And there is a concept of HR when there is no flux density. This thing is called coercive forces. This is what helps in two magnets stick to each other if they are not energized, right? So that's this. Now there are losses associated due to these phenomena, which are called hysteresis losses. So hysteresis loss is a core loss, and it's usually denoted by it usually causes temperature variation. It increases temperature, obviously losses increase temperature. So it's generally given by kh time f p max n times volume watts. Here kh is hysteresis constant, f is frequency, b max is the maximum flux density, and n is the Steinmann's constant. You'll see it to have a variation from 1.5 to 2.0, typically being 1.6. And V is volume of the conductor. There is one more thing called eddy currents. So eddy currents are currents that are are revolving currents which are produced on a magnetic surface when it's energized. So these currents also produce losses. This is also a kind of a core loss, and it's given by K times F square P max square volume watts. Right. So that's how eddy current losses will look like. So let's move on to coupled circuits. Again, I would ask you to please go through the lecture material from sir. It's very difficult to cover everything in a 2-hour class with sample problems too. So coupled circuits, let's say that, so if two or more coils are placed in close proximity to each other, let's say two coils. So what will happen? So if one coil is energized and is placed in close proximity to another coil, it will start linking the flux in the second coil too. Right. So that's what coupled circuits mean basically. So so generally this is used to transfer power from. So that's how magnetic coupling happens, right? You want to know how power, if we energize one circuit, how would it affect the other circuit too? So mm, so Dipali, can you turn off your camera? Your camera is on.
Oh, sorry, sir.
No, no, no. Hmm. So yeah, where was I? Coupled circuits. So how coupling usually looks like? Let's say we have this inductor L, and it's energized by some voltage V1, and a current is flowing like this. And if it's placed in proximity to uh, another coil, let's say with self-inductance L2, it will also experience some voltage V2, right? So, but how would this happen? Let's think in detail how usually this happens, right? So when current I flows, it produces a flux called phi1, right? Excuse my drawing, but so there is this flux phi1 is produced, which composes of phi11 and phi12, where phi11 is the flux which it links with itself, and phi12 is the flux which is being linked by the second coil. But both of these quantities are being produced by the same element, right? So yeah, so it produces phi1 flux where phi12 links the other coil. Now, according to Faraday's law of magnetic induction, what happens is the voltage is directly proportional to the n times, which is n is the number of turns of the coil, rate of change of flux, right? It's how usually we write the, it should be indifferent, right? So now, as I told, for V1, let's say, as it's linking all of the flux, it would be n d phi 1 by dt. If I write it like this, I'm just multiplying and divide di1 both sides, both numerator and denominator. So what is n d phi I by di1? It's nothing but the self-inductance of the coil, right? L1. So that's how V1 comes into picture, right? But what happens with But the interesting thing is what happens with the second coil. So what's happening is there is a coil, the component of flux which is called phi 12, which is being linked from, which is being made at the at phi 1 end, and it is being linked to the phi 12 to the second coil. So how would V2 be looking? So V2 is d phi 12 by dt. Again, doing the same thing as it's being produced by by I1 current. Here, this term is called mutual inductance, which can be written as M21. So mutual inductance of two being where one is the initiator, right? One is producing the flux for it. So this is nothing but M21 di1 by dt. Right. So that's how this concept of mutual inductance comes into picture. So if there is a current carrying if there is a current carrying conductor placed in close proximity to another inductor, it produces um, uh, it links the other coil and it produces this M21 inductance. Now, you can go through the lecture notes and you will see that sir has given a lot of material, a lot of ways on in which he has shown how. So I won't show how M12 and M21 are same. You may please see sir's lecture notes and follow the derivation to know this. Now, we came across this thing, right? We know it's M21 di1 by dt, but what is the but how do we know what is the polarity of this thing, right? Is it a positive quantity or is it a negative quantity? For this, we use the concept of dot convention, right? So by dot convention, we mean that if so we just assume that if a current enters that the point at which it enters, we call it a dot, right? And from that, we try and define how the polarity of this V2 would look like. So let's say that, just a second. Yeah. So let's say that we have a coil in proximity to another coil which is also being energized. So both of these coils are being energized, right? So now what happens? So to calculate where the what will be the direction of this magnetic field lines, what do? We use the concept of right hand thumb rule, where the thumb denotes the direction of current and the fingers curl in which direction they curl denote the direction of magnetic field, right? So since I1 is entering, so the current is going down, and the curl of the fingers will denote the direction of magnetic field, right? So it's linking like this, right? So this is phi 1. The other circuit also, it will produce something like this only. So both of these, just a second. No, sorry, it will be opposite. Yeah, right. So as you can see, what's happening is, so both of these coils are creating magnetic field in which some flux is being linked with the other coil like this for both of these quantities, right? And as you can see, just I made I didn't change the color. Hmm. Hmm. So as you'll see that both of these flux lines are adding to each other, right? They travel in the direction is something like this, right? It would be going down, and here it's coming up. It would be going up, right? So what's happening is this flux is being added to each other, right? So that's how we create this convention that when a current carrying when the current enters a dotted terminal, let's say it's entering this terminal and both of these are dots. So when it's entering the dotted terminal, what's happening is uh, the the polarity of the induced the polarity of the induced flux is additive in nature. So the mutual inductance or the polarity of mutual inductance would be positive. So has it been the other way around? Let's say if the same thing, let's assume that the dot convention is something like this, right? So we say that it should enter the terminal, right? But it's now what it's doing, it's leaving that terminal. It's going from this terminal to this terminal. So the effect is that in this side, at V1 side, the polarity of mutual inductance would be negative. So just remember, if currents are entering the dotted terminal, the polarity of that M will be positive, but if it's leaving, it would be negative. Just remember these, and sir has given a lot of examples to cover these basics too. Right now, solve some questions too. So let's see in series what happens. Series connection. So when two coils are placed in series, they with dotted terminals at the start of each conductor, what happens is the L equivalent is nothing but L1 plus L2 plus 2 times M. For other case, what would be it? It would be minus 2M, right? So you can go through those examples and you'll get to know all of these things. For parallel as well, the same thing happens. So how is the parallel connection L equivalent look like? It's nothing but L1 L2 minus M square upon L1 plus L2 minus 2M, right? So you may please go through this lecture notes and you'll get to know the the equivalent combinations of all. And there is one more concept that since this quantity has to be positive, M is generally less than equal to under root of L1 L2, and hence we defined a coupling factor which is given by M upon under root of L1 L2. So this coupling factor is a ratio between 0 to 1, generally very close to 1. So you may please visit sir's lecture and you'll get to know. So let's solve some questions so that you get a feel of how these things come into play. I'm sorry I'm moving too fast, but there's a lot to cover. Um, let's start with this question. So while doing questions, you'll get to know a lot of things. So in this question, it's saying that two identical magnetically coupled coils are tested. That is, both of them will have same in self-inductance, right? They are identical magnetically coupled coils. And the following results are found when the coils are in parallel with cumulative connection and the current through the combination is reduced smoothly from 100 ampere to 0 in 40 milliseconds. That means di by dt, which can be written as delta I by delta t, is 100 upon 40 point. Right. The total induced EMF is 220 volts. So it's saying that we know E is what? L delta I by delta t, right? So L, this is the parallel combination, can be written by E delta T upon delta
So
I.
kindly give some time, please.
Yeah. If you want to solve, you solve. Hmm. So, so, so are you solving it or you want me to
No,
take a pause?
you also solve, but after solving one question, kindly give some pause. As you were describing the concepts, you didn't give any time to write
Okay,
down.
okay. So you don't have to write down, right? I'm going to give you these notes. But then again, yeah, I'll try to. So I have a lot to cover, right? So otherwise, you won't be able to solve questions for your assignment. Hmm. So if you have doubts in this, please let me know. So dot convention, just remember that if currents are entering the terminal, the mutual conductance polarity will be positive, and if it's leaving, the mutual conductance polarity will be negative. And for series connection, again, I gave you the gist of it, but you can follow sir's lecture material to get to know how these are derived. Mm. So, did you find any trouble anywhere, or so should I continue with the question? I don't know what to do. Yeah,
Yes,
I'll
you can
continue.
continue with the question.
Yeah. So it's saying that there are two identical magnetically coupled coils,
Sir,
right? That
for the proctored exam, will the questions be similar, or like will the questions be similar to the ones which are given in the assignment? I mean, not
yeah,
similar, like the concepts will be same, right?
yeah, the concepts will be same. The questions will also be similar too, because that's what is being taught to you, right? And as you have seen that all of these assignments had all of the questions related to all of the concepts, right? Whatever was taught in that week. So yeah, if you just go through those assignment questions again and so just revisit your concepts, you'll be able to solve all of the questions in the proctored exam too. So have you registered for the proctored exam?
Yes, sir, I have registered already.
Yeah, good. So it's saying that it's an identical magnetically coupled coils. So that means the self-inductance will
And
be
sir,
same, right?
what are the minimum marks that should be targeted uh, in the entire, like 25% to 75%?
Um, I don't know what's the minimum percentage. I
No,
really
not
don't
talking
have.
about minimum percentage, but a percentage
Mhm.
which should be considered good enough, like pretty enough.
Oh, pretty enough. So what usually happens is I haven't yet ever taken a proctored exam of NPTEL, but what usually happens is they give they have this concept where they give some position to the top candidates, right? There are star performance, golden achievers, or silver achievers. I forgot. So for that, if you want to be in that and want to receive a good certificate to where your name is written with that she received this and she was a golden achiever, that's where that would come in handy. So if you can perform well, very well, that's good. If you pass this exam, anyways, you're getting that certificate, right? Which you can use in your college to get. You know, na, this MOOC course can help you remove one course from your syllabus. I forgot. It can act as a course for your syllabus too. I forgot. I don't know. But yeah, that's where this course will come in handy.
So one of the
Mhm.
teacher, not teachers, PMRF scholars like you, who also takes this course on the other day, he was asking the intent of taking this course, and he said that this course is not very like uh, not very like he replied very indirectly and directly, in fact, that this course is not like um, how to
Not
say,
like
I mean, not very
not
like,
very
why are you
good.
taking it? It doesn't have any value.
Oh, no. That's very wrong to say because I won't disagree with him fully, but then again, he's my colleague. But see, so let's say if I was a student, right, I passed out in like 10 years and I forgot what were the basic concept of electrical engineering. How am I going to revise them or revisit them? I can take this course, right? It will help me revisit everything. Then if you are in college, you missed the course entirely or you didn't study it properly and you want to know the concepts, how will that come in handy? By taking this course, right? So this course is for those people who want to increase their bandwidth and increase their concepts too, right? They want to make sure that the concepts are clear enough for them to be able to pursue further courses. So it's like it's a stepping stone, right? You can't jump into class 12th. You have to pass class 10th first, right? So that's where this course comes in handy. So there are many people. Let's say someone has done mechanical engineering and he wants to work on something that has concepts of electrical circuits. Where will he go? He'll come to this course, right? So
So
um,
not from this viewpoints, from the view of very specifically GATE exam, is this course useful,
yeah,
sir? Or
yeah. Let's say, see, what is gate? Gate also is a time bound what you say exam, right? You want to solve as many questions as possible in the given amount of time. This concepts which you are gaining right now, you are also being taught how to solve questions too, right? So when you get a hang of it, you know if this question comes, you will try to omit some steps to come up to the final answer faster. So that will only happen if you solve questions, if you practice enough. So from the gate viewpoint, you are solving 10 questions per week, 10 to 12 questions per week, right? And I should say 20 to 24, because you're also doing these sample problems too with me. So if you're doing 20 to 24 questions per week for a week, do you per week for a course, what do you think? Isn't it a good idea?
yes, it will be.
Yes, right. Instead of doing everything at the end of your fourth year, right? You're doing it together with as your this BTech degree progresses. So it's a good thing, right? That's what I feel. So I usually used to do the opposite. I used to solve everything before my exams, which is not a good thing to do, right? You have to solve continuously to be able to do well in exams. And solving continuously, you can know how to solve questions faster too. And if you see, you would feel right, I can solve questions faster than you. I don't have solutions for this. I also solve it with you, but I can solve it faster than you because I have experience. So and experience only comes by solving questions. So that's what's happening. So am I clear?
Okay, sir. So he also said that after this, there won't be any point taking any courses if your professors are good enough. But like in the first year, initially the research scholars teach you half of the subjects, and then there the assistant professors do take. So
Mhm. I am also a
is he?
research scholar. I'm in my second year of PhD, so it's like I mean, it's not like I'm teaching you bad, right? I don't know. I think I'm being honest with what I'm doing. So I don't get you. So what were you trying to say? What was your point?
The point is that whatever he said, that there is no point in taking the courses if your professors in your university are good enough, because you're already getting that basic electrical engineering paper credit from your university also and from NPTEL also. So what is the difference that you are doing it additionally?
So see, I would like to disagree with him, but then again, it's his viewpoint, right? And some people would feel like this won't add much to their pursuit of gate, right? But for some, it's more like clarity of concept. So, and I usually feel that if you have clear concepts, if you have clarity of your concepts, you will be able to solve questions, any questions that's thrown to you. So it's more like quality over quantity. And I what I feel is with the questions that you are solving are quality questions. So they are not like your in your gate examination books, right? They have this hundreds of questions on a single topic, right? And those don't have quality. Those only have quantity. More questions with less reliance on how they are going to be solved. So what I feel is this is getting you ready with the concepts, necessary concepts, which you can use to solve gate exam. So It's up to you, Renessa. I mean, it's how good of a hardworking individual you are to be able to solve these questions. So if you do the hard work right now, you will be able to solve it in your GATE exams. I don't feel the what you say. Um, I don't feel as if it would not help you in GATE. It's not what I feel. I feel that this course is going to help you in GATE exam too. Many of my friends used NPTEL to clear their GATE concepts, and it's so. And one more thing, NPTEL concepts are available on YouTube free of cost, right? Anyone can watch them. Anyone can do this stuff. And if you're getting a certificate out of it, why not get it? That's what my point is. But then again, everyone is entitled to
So
their
it is the
opinions, right?
thing is that what is happening is that you have like too many papers to clear in this semester also, and
Mm,
this paper is an additional one, right? Like
mm,
another one also. So
mm.
that is
So
what you said is quite
yeah,
stressful, and you don't need to take it.
yeah. So yeah, let's do one thing. And I'll just complete the questions for this class because most of people depend on these classes to solve the assignment, right? And then we can continue what you want to discuss after the class, right? That's okay for you?
Yeah, that's totally fine.
Yeah. So let's solve this question, right? So what this question has said is that two identically magnetically coupled coils are tested, and what's found is that when the coils are in parallel, the current through the combination reduces smoothly from 100 ampere to 0 in 40 milliseconds. That means delta I by delta T is given, right? 100 upon 40 milliseconds. And the total induced EMF is what? 220 volts. So from the concept of self-inductance, we know E is nothing but L di by dt, right? So can we get L, which is because it's connected in parallel, I have denoted it as L parallel. So can we get L parallel from it? Yeah, we can. So can you tell me what's the answer? It would be 88 millihenry, right? Now the same thing is happening over here. They have now tested it with series, um, differentially connected differentially in series. That means they are connected like this. So the current is entering for one inductor and leaving for the other, right? And the formula of what is given by L1 plus L2 minus 2M, right? So what is the L series? It's saying that the total flux linkage is found to be, okay, let's denote flux linkage as lambda in phi, right? 0.016 and current is 8 ampere, right? Now we know L can be denoted as N phi I, right? N delta phi upon delta I, but since it's given a single quantity, we can write it like this. So that means L series is what? 0.016 divided by 8, which is 2 millihenry, right? Now, uh, so we know that from the concept that uh, L series is what? 2L minus 2M, right? Because it's a what you say differentially connected in series, right? And both of the self-inductances are same. So that means L minus M is nothing but 1 millihenry. Also, a parallel combination is given by what? L1, sorry, L square minus M square, L1, L2, 2L minus 2M, right? That's how it's given. So that means if I write it like this, L plus M, L minus M upon 2 L minus M, which is what? L parallel is 88. So L plus M comes out to be 176 millihenry. So from this, you can get the inductances, right? So what is L? L is nothing but you add both 177 upon 2, which is 88.5 millihenries. And M is what? 87.5 millihenries, right? So we are required to find coupling factor, which is given by M upon under root L square, which is M upon L. So this comes out to be 87.5 divided by 88.5. This is 0.988. So which is the answer? It's D part. So any doubt? So it's simple, right? I just saw what kind of tests they conducted and followed the results, and I got the value of coupling factor. Let's move on to next questions. This is a good question. So what's given here is that we are required to in this circuit we have an AC voltage, and the current through from this voltage is in phase with it. That means there is no imaginary part in that in for that impedance. And it's saying if the coupling coefficients between the coil is denoted by K, find the value of K and the dot polarity of PQ. Okay. So how are we going to solve this question? So it's simple, right? So uh, yeah, just a second. Yeah. So V and IT are in phase. So that means the equivalent uh, impedance has only the real part. So let's redraw the circuit. So this is minus J4. This is 29 ohms. This is 20J. And this is J12J. So what happens in a series circuit? We have a voltage source with 2 times Jm, right? So that's what we get over here, right? So now what I did was I just wrote the polarity like this, right? Plus minus. I didn't check what exactly is it's going to be. Just assume for a moment that the polarity of the equivalent voltage that comes out from that mutual inductance is like this only. So let's calculate. Let's do a loop KVL across it. So that means minus J4I plus 29I plus 20J times I. I is current over here plus J12I and minus, there has to be a current component too, right? 2MIJ. So let's rewrite it. It would be like 29I minus plus J. This is 20J, 32J. 32 minus 4 is 28. So 28 minus 2MJ. Sorry, 28 minus 22 minus 2M. So what is VI, which is Z, which is 29 plus J times 28 minus 2M. So therefore, what is 2M? It is 28. That means M is what? 14, right? So now we can calculate the coupling factor. It is nothing but M upon under root of L1, L2, which comes out to be this. Okay, so J omega L, right? Omega will anyways get cancelled, so we don't have to worry about that. So it's 20 into 12, right? So what is this? So you must be thinking that I simply multiplied it, right? So Renessa, can you tell me? So I simply just took these values, but these are J omega L, right? So why haven't I removed that omega before? Because we are required to put L only. It's because this M also contains frequency component. These also contain. When we divide it, it would vanish, right? So we don't have to worry about it. We can simply just use this 2. So K comes out to be 0.9. So what are the answers? Okay, so A and D can be the answers. B and C are gone. So it's saying that at what polarity should the dot P be kept. Now, since I've added this, this is being subtracted from the, so I took this polarity, right, which seems to be correct because the this M is positive for that polarity. And that's what we wanted, right? Had it been negative, we would have to reverse the polarity. So if that's the case, what's happening is it's differential, right? So that means the dot must be kept at which position? Vanessa. The dot must be kept at which position? So it's already a differential circuit, right? So that means if it's leaving this terminal over here, then it has to be kept at this terminal. So that it one inductor it's leaving and the other it's entering. That's why it's in a differential terms. Any questions, Renessa? So what I did, I wrote the equivalent circuit. I took any polarity that I wanted, which was 2mji, and then I used the circuit to formulate what would be the equivalent impedance, and from that I got the value of k, and from that, as my m was not negative, my polarity was correct, and since my polarity was in differential, the dot must be kept at p. Okay, so is it all right? Shall we move ahead? Okay. So what we are required to do is we are required to form the equivalent impedance. How would the equivalent impedance look like, right? So let's see for this circuit. Let's uh, let's write KVL for this circuit. What is it? It's Vs equals to 50 times I1, right? Plus, if I write, it would be J times omega is 5,000, right? 5,000 into 5 milli is 25 only, right? So 25 I1 won't be visible. This is equals to 50 I1 plus 25 times 25 I1. Now, the what's happening in the other circuit, it's entering this terminal, right? But this here as well, it's entering. But the position is what? This is positive, right? Because whatever the polarity of the dot is, the polarity of the the other part of the circuit will be, and since it's kept in the opposite direction, the equivalent would be a negative, right? So it would be minus j times 20 I2. And the other part is nothing but 10 times I2 plus J2 into 5 is 10. 10 I2, and then this would also be minus, right? J20 I1. So let's write I2 in terms of I1. So I2 would be what? 20 J I1 divided by 10 plus 10J, right? Let's normalize this. This would be 20 iota upon 10 plus. So this is nothing but 1 plus 1 iota, that is is 1, this is 2. Equate 2 in 1. What happens is Vs is nothing but 50 times I1 plus 25 times I1J minus J20 and minus J and J are negative. This would be plus 20 I1, right? So Vs is what? 70 I1 plus 5 I1. So equivalent impedance is nothing but 70 plus J5. See how easy it is to solve these questions. Just remember the polarity and try to solve it like normally you would do for the AC circuit analysis, right? That's what you do here. Okay, let's do one more question. So you have this circuit. Um, what we have is that networks of question 6.1 and 6.2 are equivalent. That means this circuit and this circuit are similar in nature, and we are required to calculate the values of L1, L2, and M. So how can we do it? Let's say that if these are equivalent, let's call this as V1, the current flowing is I1, and this would be V2, the current flowing here is I2. Similarly here, this is V1, I1, V2, I2. So what's happening is for the first circuit, let's write for first circuit. Vs is equals to J omega times 0 point J omega times, let's write it as 30 only, 30 I1 plus J omega times 15 I1 plus I2. That means it's nothing but J omega 45 I1 plus J omega 15 I2. Similarly, V2 for the first circuit can be written as J omega 115 I1 plus J omega, sorry, I2 plus J omega 15 I1. Now for second circuit, V1 is equal to what? J omega L1 I1 plus J omega M I2, and V2 is J omega L2 I2 plus J omega M I1. So if you compare these four equations, what you get is the equivalent value of L1, L2, and M, right? So that means L1 is what? 45, L2 is 115, and M is 15 millihenries. So the right answer is C. So that's how you solve these questions. So I'm sorry I couldn't solve all of them, but I tried to solve most of them. So please go through the lecture material because it's very difficult to cover a week's lecture in just a single class and solve the sample problems too.
Yeah, so I was just thinking to add two more questions so that the assignment is done for week 10. So there's one question. So in this question, a magnetic circuit is given which has the dimensions where the core and the air gap have this similar cross section area. The air gap length is given to be 0.050 centimeter, and the length of the flux path is 30 centimeter, and number of coils are 225 turns. Also, we are given relative permeability, which is 70,000 for the core material. That means mu is going to be mu naught times mu r. And also we are given BC, which is 0.9 Teslas. Now, as I've already taught in the class, to do this, what we do is we form parallels between electric circuits and magnetic circuits, right? So in this, there are two kinds of reluctances. One is the reluctance of core, just a second, and the other is this reluctance of this air gap, right? So let's first try and calculate the reluctance of core, right? So what exactly is reluctance? Reluctance is nothing but Lm upon A times mu, right? So what is Lm? 30 centimeter. Let's convert it into meters. and area is given to be 16 centimeters square. Let's also convert it into meters, and then mu is what? Mu naught times mu r, which is 4 pi into 10 raised to the power minus 7 into 70,000. If you calculate it, it comes out to be around 2131.54. Okay. Yeah, so it's now similarly for the air gap also you can calculate. Air gap is what? Lg times Ag mu g, which is nothing but so we are given g as 0.050 centimeter, 10 raised to the power minus 2, Ag is 16 over 10 raised to the power 4 into mu naught only, right? Because mu g is mu naught, which is 4 pi into 10 raised to the power minus 7. So what if you calculate it, it comes out to be 248,679.6. Now, as I've already told you to so you form a parallel between the magnetic circuits and an electric circuit, and the driving force is your MMF, magnetomotive force, which is driving the flux around these two reluctances, right? Rg and Rc. So we are required to find the current which will flow, right? So we know that we're given BC, right? BC, which is the flux density of the core, which is 0.9 Tesla. We know phi is what? B times A, right? So let's calculate it, which is 0.9 into, this is Tesla. A is 16 upon 10 raised to the power 4, right? This comes out to be 1.44 into 10 raised to the power minus 3. Now okay, now we know Fm is what? Phi times Rc plus Rg. Now magnetomotive force is given by N times the current I, phi times Rc plus Rg. So we know all of these variables, right? Phi is 1.44 into 10 raised to the power minus 3. Rc is what? 2131.54. And you have 248,679.6 divided by N, which is 225, right? So here you can calculate I. Let's do it. It's just a second. Times 2131.54 plus 248,679.6 divided by 225. So it's 1605 multiplied by 10 raised to, so 1.605, right? Amperes. So we're required to find in milliamperes, so it's 1605 milliamperes, right? So it's A. That's done. Now there's one more question that I want to discuss, which is this. In here we are given that there is an iron ring which of mean length is 60 centimeter, has an air gap of 2 millimeter and a winding of 100 turns. The iron has a permeability of 1.25 into 10 raised to the power minus 4. So let's write it. Mean length is given 60 centimeter, gap is of 2 millimeter, winding is 100 turns, permeability is 1.25 into 10 raised to the power minus 4, and the current that it's carrying is 1 ampere. So we are required to find B. Okay, let's do it. So we have everything, right? So let's calculate the reluctance of core, which is what? Lc upon A C into mu. 0.6. We don't know the area, so let's keep it as it is. 2 raised to the power minus 4, which comes out to be 4800 upon A. Similarly, Rg is what? Lg upon A times mu naught, which is 1591.55 upon A. Right. So Yeah, so I've already calculated these values, just confirm these ones. I mean, if the answer comes out, it's already confirmed, but still. So Fm is what? Ni, which is what? 100 ampere turns, that's what we are given. 100 turns and it's carrying a current of I. So we can calculate flux. Flux is what? Fm upon Rc plus Rg, which is 8 times 0.0156. Now we know B is what? Phi by A, which is 0.0156 Tesla, or 1.15.6 millitesla, right? We are required to find it in milliterms, so it's B. So that's how you solve these kind of magnetic circuits. What you do is you form parallels between electric circuits and magnetic circuits, find the reluctance, and then just solve as is what you did for what you have done for the electric circuits, and you will be able to come up with the answers. So that's it. I just wanted to add these two questions too, so that the assignment is fully completed. I would request you to please go through the lecture and the material provided by the instructor. And if you still have doubts, you can raise your doubts through that Google discussion platform, and we'll be happy to help. Thank you.